Okay, quiz 16.1 is sort of a qualitative look at acids and bases. In the first question, we're asked to list the conjugate acid for each of these bases. And remember, the difference between the conjugate acid and the conjugate base is the presence or absence of an H+. So these are bases. We'll just put an H+ onto them, and that will be their conjugate acid. So for example, NH3 would have NH4+. CO3 2- would have HCO3 with just a 1-. HCO3 1- would be H2CO3. NO2- would be HNO2. ClO4- is HClO4. HPO4 2- we'll add an H+, get H2PO4 1-. HSO3- would be H2SO3, and F- would be HF. So when some of these had an H+ added, they became neutral. Some of them just had a negative charge that was less than what it had been before. And then this is one interesting example where it actually goes from neutral to positive. Okay, we'll scroll down to the next question, which is just kind of the inverse. Give the conjugate base for each of these acids. So now we'll be removing an H+. So HCO3- becomes CO3 2-. H2SO4 becomes HSO4-. HSO4- becomes SO4 2-. HBr becomes Br-. H3PO4 becomes H2PO4-. And then H2PO4- becomes HPO4 2-. And then HPO4 2- becomes PO4 3-. And HIO3 becomes IO3-. And some of these are obviously parts of multiprotic series. So H2SO4 to HSO4 to SO4 2-. That's a multiprotic series, as well as the phosphoric acid series, H3PO4, H2PO4-, HPO4 2-, and PO4 3-. Okay, so that was just a ton of examples. Hopefully this is something that is really easy for you to predict what the conjugate acid or base would be, and to recognize conjugate relationships between acids and bases if you see them. Oh gosh, I keep scrolling the wrong way. This is funny. One of my computers scrolls with fingers up, and one of my computers scrolls with fingers down, and so I can never seem to get it right. Okay, predict whether the predict the products for each acid-base reaction. So we're going to have HNO3 plus H2O. And our task here is to identify which is going to be the acid and which is going to be the base. Well, HNO3 is a strong acid. Water could go either way, but the strong acid is definitely going to be what's acting as the acid. So what do we have? H3O+, the conjugate acid to water, and NO3-, the conjugate base to nitric acid. What about NaOH plus HCl? This one's also pretty easy to identify which is the base and which is the acid. HCl is one of our 7 strong acids. NaOH is a group 1 hydroxide salt. That's one of our strong bases. And so the acid will donate a hydrogen to the base. Now, because NaOH is a soluble salt, what we'll really have is the Na separated from the OH, and we can go ahead and pair it with that chloride left over, NaCl. And then the H is going to go pair with the OH to form water. So a strong acid with a strong base is going to leave behind some ionic compound, we'll call it a salt sometimes, and water. All right, ClO minus plus HNO2. And here we have ClO minus does not have any hydrogens to give, so it must be a base. And then HNO2 is a weak acid. Perhaps you're not familiar with it, but it does have a hydrogen listed first. And so that's a signal to you that this could act as an acid. And so this will be the acid, this will be the base, and we'll be left with HClO plus NO2 minus. And this one, in all likelihood, will be an equilibrium reaction. Okay, let me actually put up a question that I did not ask. What if I have something like HSO3 minus plus H2PO4 minus? Okay. Here we have amphiprotic species. This could act as an acid or act as a base. This could act as an acid or act as a base. So how do we know which way it's going to go? And it can get complicated. We would need to look at the specific acid and base strengths, and the reality is every combination will happen. HSO4 minus acting as the acid and H2PO4 minus acting as a base will happen. And then HSO3 minus acting as the base and H2PO4 minus acting as the acid will also happen. They'll both happen simultaneously. There's nothing to prevent that. Usually one of them will happen like to a much greater extent and will be the sort of dominating reaction in this system. But it becomes very messy when you have like several amphiprotic species. That's going to explode into all sorts of complex side reactions. They'll also both be reacting with water. In the end, your solution will have every member of both of these multiprotic series present in some concentration. There will be phosphate, phosphoric acid, hydrogen phosphate, dihydrogen phosphate. There will be sulfite, hydrogen sulfite, and sulfurous acid all present simultaneously in the solution, and it would be a big mess and a headache. So that's why I did not give you that problem. I did not assign this problem. Okay. Ooh, guessed wrong again. Okay, question 4. For this one, let's just look at it. We have conjugate acids and bases here in all of our reactions. And the trick is to identify where hydrogen has been transferred in both the forward and the reverse reactions. Even if it's not written as a reversible reaction, it should still be, we can still consider the hypothetical scenario of if this did go in reverse, how would a hydrogen be transferred in order to identify the conjugate acids and bases. Okay, so let's look at this one. We have HCO3 minus plus HSO4 minus. This is an example where it would be difficult to predict the products, but thankfully we were given products. We have H2CO3 plus SO4 2 minus. Okay, so moving in the forward direction, what happened? It looks like the hydrogen sulfate donated a proton to the bicarbonate. And in the reverse direction, it looks like carbonic acid donated to the sulfate ion. So here we have our acids. Here we have our bases. And then which ones are the conjugate pairs? bicarbonate with carbonic acid, that's a conjugate pair, and the hydrogen sulfate or bisulfate and the sulfate ion, they are a conjugate pair. All right, the next one, we have water plus water in equilibrium with H3O plus and OH minus. Okay, so the reverse direction is easy to tell. The H3O is going to donate a hydrogen here. Over here it's actually ambiguous, it's arbitrary, it doesn't matter. One of them is going to give a hydrogen to the other. And position, left or right, doesn't mean anything in chemical equations, so it is totally arbitrary. I chose to have the left one give a hydrogen to the right one. That makes this an acid, and this one a base, and this an acid, and this a base. And so there's one pair, and there's the other pair. And I don't think I have room to do the third one below. Let's show the third one. Okay, so we have HN3. That's a typo. That doesn't make any sense. That should be NH3. The NH3 plus H2O in equilibrium with NH4 plus plus OH minus. And so we're going to have water donating to the ammonia on this side, and ammonium donating to the hydroxide on that side. So we have acid, acid, base, base, and those two are a conjugate pair. They differ only in the presence and absence of an H plus, and these two are the conjugate pair. Okay, the last question, right down there at the bottom, says HNO2 is a stronger acid than HF is. What can you say about the relative base strengths of nitrite and fluoride? So we have HNO2 and NO2 minus. They are a conjugate pair. I'll represent that with a double-headed arrow. And then we have HF and F minus. They are a conjugate pair. And remember, the acid strength and the base strength of a conjugate pair is limited. It's bounded to a certain value. And we're so close. In the next section, we'll finally talk about what that value is and deal with this mathematically. But for now, we just know that it's limited. And so the stronger one partner is, the weaker its conjugate must be. So if HNO2 is stronger than HF, then we'll say this is stronger and this is weaker. Now I don't know by how much. Maybe that's a really close match, or maybe HNO2 is much stronger. I don't know. But HNO2 is stronger and HF is weaker. That means that NO2 minus as a base is going to be weaker than F minus. F minus will be the stronger base. HNO2 is the stronger acid, and they're balanced in this way.